I'm recording and I do have audio, and we ain't going to say nothing else about my gangsta background on video. I'm from Louisiana, that's right. It's like I actually have a letter at home framed hanging on my wall from Vice President Dick Cheney. It was when he shot that guy in the hunting trip. He accidentally shot his lawyer friend. And everybody in the media was giving him grief. So I sent him a letter and said, Mr. Cheney, next time they give you grief about this, just look them in the eye and say, hey, we were in Texas, he was a lawyer, he was in season, shut up. And he actually wrote me back. It's kind of a nice feeling when you get a letter from the Vice President of the United States. But anyway, let's talk about physics, because that's what I'm getting paid to teach you about. You okay, Cyrus? You okay? Everybody sign in? Anybody not signed in? Okay. Well, I was just a teenager then. It was, I don't even remember the name of their school, but their band was beating up our band, and their football team was beating up our football team. And the guy kicked me in the leg, or so I thought. Turned around, there he is with pointing the gun at me. I took it from him. Yeah, I played first trumpet. Marion High School, Lake Charles, Louisiana. Anybody have any questions about how to do vectors and E-fields? How's that lab coming? Everybody got a handle on it? Now it's just the tedium of the repetition. Sure, everybody good with it? Okay. I know. It's consolation prizes. It's the big one for the semester. Get past it, and that's everything else is going to be smaller in comparison. But it really is a crucial concept for you to get. And I don't mean just be able to figure out how to solve the homework problem. I mean to understand E-fields, vector fields, how they relate to the potential, that the electromotive force. You're about to find out when we get to Gauss's law that if you don't have a good grasp of this, everything else from here on out is going to get real confusing real quick. So it's very important to get a good grasp on this subject. And that's why I made the decision to do this lab this way. All right. Well, then that brings us up through 16.6, and we talked about the electric field already. I don't know who teaches statistics in here, but he needs to start cleaning up after himself. Yeah. We know Coulomb's law. Force, the electric force between two charged particles, K, Q1, Q2, over R squared. That's the force that Q1 exerts on Q2. You could also say it's the force that Q2 exerts on Q1. That's an arbitrary assignment. If you have two charges, both of them are going to produce an E field. And the net E field flux at any point in space around them is going to be the vector sum of both of those E fields. We also define the E field such that, make these vector equations, define that E field such that the E field times a charge, in this case we'll say Q2, is equal to the force, the electric force that charged particle is experiencing. Well, this force, we set these two equal to each other. We know what that force is, KQ1, Q2 over R squared. And we can solve for E by dividing both sides by Q2. They cancel out, and we're left with the expression for our electric field is equal to K times Q over R squared. That is the mathematical expression for an electric field. Now, I wrote it as a vector equation. But you should also understand that with electric fields, there's positive and there's negative. Okay? So, if it's positive or negative, if two charges are alike, they push against each other. If they are different, then they attract each other. And by standard, we say that the field lines generated by a positive charge point away from it, and the E field lines, or lines of flux, whatever you want to call them, on a negative charge, point towards it. What does that mean? That means that if you put a positive charge right here, this force, the vector, the field, the E field from this charge is going to push it away. And the E field from this charge is going to pull it towards it. And as you're learning from the lab, the total E field that this charge experiences at this point is equal to the vector sum of the two component E fields. Now, I or talk a little bit. Everybody finished taking notes? Any of that they want to copy down? Pretty sure at least one of your homework problems is going to be to draw the E field lines between, from a point charge or to a point charge or between 2 point charges. And you just saw how I drew them. Drew a circle, put a sign in to indicate is it a positive charge or a negative charge. Draw lines radiating out in all directions. Put the arrows, if it's a negative charge, point the arrows towards it. If it's positive, point the arrows away from it. So, let's say, let's do it positive. Say we've got 2 point charges. They're both positive. Let's use 6 lines coming off of each one. 1, 2, 3, 4, 5, 6. 1, 2, 3, 4, 5, and 6. How would those lines, how would that E field form? Well, middle, they're going to push apart from each other. The rest of them are going to go radially out in all directions. I'm pretty sure you'll see some pictures that look a lot better than I can draw in the book. That's what happens when you have 2 like charges. You could fill in more lines in here if you wanted to. They would keep doing this. No matter how many you fill in. They're just going to push apart from each other. So, and if you found the actual mathematical center right there, and you calculated the vector sum of the 2 E field components from both charged particles and added them together, you would find that right here you truly do get 0 E field. You get a little bit off. Now this one is pointing this way. This one is pointing this way. How do you draw the 2? How do you combine the 2? Well, break it down into horizontal components and vertical components. The 2 horizontal components cancel each other out. The 2 vertical components add together. And so right here, you end up with a very small E field pointing that way. You go a little above the geometric center, the exact center, and you're going to start getting small components pointing up. The further up you go, the larger those components will get. What happens if we draw a positive and a negative charge? Put a positive charge here, a negative charge here. Again, they're the same charge, so we'll put the same number of lines on both of them. 1, 2, 3, 4, 5, and 6. 1, 2, 3, 4, 5, and 6. And we'll go ahead and add a 7th one. Now, how do these lines form up? Well, in this case, they go straight to each other. It's like that. You will notice right in the center, down here, you're going to have a perfectly, if you're exactly at the midpoint, down here, the vector is going to be perfectly horizontal. Same up here. Anywhere along this midpoint. at the midpoint, the vectors will be perfectly horizontal. Because you're going straight from positive to negative. Come back this way a little bit, they're going to be pointing up slightly. The further this way you come, the more vertically they're going to point. You go that way, they're going to start pointing down. Right in the middle, they're going to be pointing straight across. And that should be what you're starting to see when you fill in that vector field on your graph. There's one more they show here. Let's do this. This is one I'm pretty sure is going to be in your homework, and I want you to see how to do this, make it look good. Say we've got a negative charge over here, and a positive charge over here. But let's suppose that the positive charge is 2Q. It's twice as much as the negative charge. So you've got Q, a negative charge, and 2Q, positive charge, twice as much positive charge. Now, how would you graph these lines? Well, start off like we did before. You've got, say, let's put 6 lines on the negative charge. But because the positive charge has 2Q, twice as much charge, we'll put twice as many lines. So we'll go with 12 lines coming off of it. Now, to draw your vector field, connect lines. I don't even draw it straight out that way. But you'll see that it's going to produce a teardrop shape in that vector field. Does anybody have any questions so far? They just go out into space. Yeah, the idea here is that if you can match up, it would have actually worked better if I'd have drawn these. If I'd have drawn these pointing up and down and these tilted this way, because then I could have had one coming down here, one coming over here. It would have looked more. You'd have seen that that this one gets tied up, but all the extra charge on this one fans out around it. The idea here is that you draw the number of flux lines proportional to the amount of charge that you're dealing with. Twice as much charge, twice as many flux lines. And they all go somewhere, even if they just point off into space. That's the thing about these flux lines. We talk about it as a flux, and we visualize the E field as lines of force. In the same way that we visualize vectors as, little arrows, but that's not really what they are. A vector is a force, it's a magnitude with a direction associated with it. Okay, and so we will draw a little arrow pointing down and say this is mass times gravity. but that's actually just a visualization. And we can make the arrow longer to show that it's a bigger force, or shorter to show that it's a smaller force, but it's still just a visualization. The same thing is true with these vector fields, the E fields. It's a visualization technique, and we can envision that the more lines we put, the stronger the field is, the fewer lines, the weaker. And talk about how dense those lines get in terms of a flux. Okay. But again, it's all visualization. As you're learning from this lab, you pick a point in space, any point in space, and you can calculate the direction and magnitude of that E field force vector at that point in space. And those vectors will start to form this kind of a pattern. But it's important to understand that this is just a visualization technique. Okay. That in fact, there's going to be some E field force vector at every point in space around that charge. We're only drawing in a subset of them, just to give you a picture of what the field is shaped like. Now, any questions? Is anyone having any trouble with the homework yet? No? Okay. What if we have two conductive plates? Yeah, we charge this one to plus Q and this one to minus Q. How are the E field lines going to form between them? Well, from here, go straight across. And it's going to do so in a uniform fashion. Up till you get to the outside edge. And then it's going to start fringing. But anywhere between those two plates, as long as you're not anywhere near either edge, you're going to have a nice, constant, uniform electric field, all pointing in one direction. Why does that happen? Again, this is we're getting to a very important concept here. So if this doesn't make sense, if you don't get it, speak up. I will try to explain better. The first thing you need to understand is that anytime you have a conductive surface, a metal or some kind of conductive surface, if it's charged, the E field that emanates from that charged surface will always be normal to the surface. That means perpendicular to the surface. Okay? Think of a metal sphere. Okay? Now let's put some electric charge on here. We put some extra electrons right here. They congregate on the surface here. What's the first thing they're going to do? They're going to repel each other. So they're going to immediately spread out. Put the maximum distance between each of them that they can. Okay? So the charge is immediately going to uniformly distribute itself over the surface of the field. the conductor. Now, let's look at this conductor surface here. Imagine that there's an electric field emanating off of this surface, but it's at an angle. It's not coming off perfectly normal to that conductive surface. Yeah, this is the E field emanating off of this conductive surface. And just as a thought experiment, we're going to pretend like it's coming off at some arbitrary angle. Okay? That it's not perfectly normal to the surface. Well, what does that mean? What will happen? It means we can immediately decompose this vector, this E field vector, into two components. One component that's perfectly normal to the surface, and a second component that is at that point parallel to the surface. Okay? Well, what's going to happen if we have a component of that E field parallel to that surface? There's a little charge here that's producing that E field. There's another charge here. Well, if there is a net vector here pushing in that direction, it's going to push that little charge further away. You see how that's going to happen? But every charge on that sphere's surface has already redistributed itself until they've all come to rest. They've all stopped moving apart so that they're all uniformly distributed with maximum distance between them everywhere. That means if there is a component of whatever component of E field this charge is pushing in that direction with, there is another component over here pushing opposite it. They're all canceling out. You see how do you understand what I'm saying? That if there is a tangential component to that E field at that point on the surface, it's going to push around that charge, those extra electrons, until they redistribute themselves to get rid of it, to make it go away. Okay? Because they're all going to come to rest, and once they're at rest, there can be no net force acting tangentially on any of them. Because if there was, then they would continue to move until it went away, till it all got canceled out. That's why we know that anytime you have charge on a conductive surface that is generating an E field from that conductive surface, the E field generated will always be perfectly normal to the surface at every point. And by normal, I mean perpendicular to the surface at that point. Everybody see why that is true and how that works? Okay. Now, we also know that anytime you have a conductive body, a conductive material in an E field, the net E field inside that conductor, as long as there's no moving charges, as long as we're talking about static situations where the charges are not moving, that E field has to be zero. Why? Because if the E field inside the conductor were not zero, then the charges would not be static. They would be moving, and you would have an electric current. See what I'm saying? So, look on page 459 at example 1636. Look at that figure. Let's analyze that picture. See if we can tell what's going on. We've got the two conductive plates, and we've got a conductive tube, rectangular tube or shell or box or whatever inside between the plates. All right. Now, let's charge this plate to Q and this one to minus Q. Now we're going to get some fringing down here at the edge. But then the E field is going to quickly become uniform and constant, going straight across. What's happening? This is positive. These are all negative. What's happening here on this box? This has to be negative. That's right. This positive E field is attracting free electrons in this conductive box. This side becomes positively charged where those free electrons got pulled away from. What about on this edge here and here? What is this E field line doing that passes right next to that edge? Not doing anything. It's passing parallel to it, right next to it, right up to the edge of it, but the E field line does not terminate on that box. Nothing happened. In fact, you would find that this edge and this edge would stay neutral, uncharged neutral. All of the electrons needed to terminate the flux lines coming in from this side will be drawn from this side as needed. And you'll get your matchup. You'll get your balance of charge from here to here, whatever net. If this box is not charged to begin with, if it's net neutral when you put it there, when you put it in, it's going to stay net neutral. There's no electrons migrating across collecting on it. So any electrons that need to be pulled over to this side get pulled over from that side. So you have a net positive charge on that side, balanced by a net negative charge on this side, so the whole box stays net neutral. Just like that gold bar in the homework assignment. You got mega amps worth of coulombs of charge of electrons in that 12 kilograms of gold. But you've got the same number of protons. So the net charge of the bar is 0. Same thing here. Also notice there's no E field inside the center of that box either. Why would there be? There's no E field inside this conductive surface, inside this conductive body. Now, initially, when you first stick it in there, there's going to be some migration of charge because the charges are going to move from here over to here. But once they've moved over and everything's become static, there's no E field in here, which means there's no moving electrons in here, which means it stays just empty space. There is no E field inside. That's how EM shields work. That's why you can take a metal cage, a Faraday cage, and put it around a radio, a cell phone, and no signal can get to it. Oh, here on page 459, they show the figure 1635 shows what I was telling you about a minute ago about how if you assume that the E field off of the conductive surface is not normal to the surface, what happens? And they go through and give you an explanation of that. Might make it a little more clear than I did. Now in this case, there is no net charge inside this inner box. So there's no E field inside there. Let's take a look at another example. This time we've got a hollow conducting sphere. And inside that hollow conducting sphere, we put a minus Q charge. Oh, look at that. They ought to hire me to slice pizza. There's all our E field lines coming off of that central, that contained charge, minus Q. So what happens where that E field line intersects with that conductive surface? What actually happens is it's going to repel an electron away from an atom. One of the free electrons is going to be repelled away. But we can also just think of it as it's going to draw in positive charges everywhere those E field lines meet that surface. Well, where do those positive charges come from? Or thinking of it the other way, if you think of it as it's repelling free electrons, where do those free electrons go? They get pushed over to the side, to the other surface. And start producing their own electric fields. Everywhere perfectly normal to the surface of that conducting sphere. Now, let me ask you a question. Just looking at this drawing and pretending for a moment like it's a good drawing. Okay. If you were out here and you measured the E field produced by this construct here, how would this E field differ from this giant conducting sphere as opposed to just if it just had that 1 point charge Q? How would it vary? How would it differ? Somebody guess. well, yeah, there would be a vector, an E field here, yeah, an E field vector here, yes, and it would be pointing towards the negative charge. My question is, how would it be different from this to this? Where over here, we've got this point charge Q, minus Q, contained in this big sphere. And here, we've just got just the point charge Q. Now, if we come out to this same position and measure this E field vector and compare it to this E field vector, how will the two differ? No, yeah, I'm talking about the angle of the vector, the magnitude of the vector. Those are the only two properties you can measure. You can measure an angle and a magnitude of this E field at this point, right here, relative to this point charge Q, or relative to that same point charge Q with a giant conducting sphere around it. That being the case, how do you think those two vectors would measure differently? It's a trick question. The answer is it would not be different. There would be no difference between them. This E field vector here would be exactly the same as this E field vector here. This giant conducting sphere will have made absolutely no difference whatsoever. In this case, what it makes a difference to is in this region here, inside this conducting sphere, you have a field-free region where there's no E field inside the sphere. Okay? Inside that sphere. The sphere itself is still net neutral. There is no net charge on the sphere itself. Whatever negative gets redistributed on the outer surface is completely offset by the positive redistributed on the inner surface. Now, what I have done here is snuck right up behind you with what we're coming to next, and it's called Gauss's law. And what Gauss's law says is what I just told you, that there's no difference between these two, between this E field vector and this E field vector. That if you measure, if you take and you calculate and integrate all of the E flux passing through this closed surface around this whole region of space, then if you add up all the little delta E fields passing through over all the little delta pieces of surface, you sum it up over the, really it would be an integral equation when you get to the continuous version of it. So you'd be integrating over the entire closed surface, but all an integral is just adding up a bunch of little infinitesimally small pieces of sums. So you sum up all of that flux passing through that whole surface, and it will equal a constant times the charge that's enclosed within that Gaussian surface. And we're going to talk about that more next time as we talk about flux passing through surfaces. I don't have time left today to do it, to really get into it any further than that. So I'm going to, one more time, open up the floor to questions about the homework, about the material we've covered so far. Test on Monday. We still need to finish chapter 16 here, which means we need to do Gauss's law, because you're going to need to do Gauss's law. Gauss's law is 16-12. We're going to be skipping a couple of sections. DNA, nucleotides, and photocopy machines, but we are definitely going to cover Gauss's law. We'll do that Monday in class. So everybody get your lab done and get your homework done and ready to turn in on Monday. Be ready to finish your homework in class as we go through the Gauss's. Any problem that relate in your homework relating to Gauss's law, we'll work them in class as we cover the material, so you can hand in your homework in class on Monday on time. And then I will give you the exam to take home and finish and turn in on Wednesday. And we'll be caught up. Okay? Sound like a plan? Then have a good weekend.